Hi, I am Michael. Today, Henry, Jianyong, and I will introduce the latest progress of Cloud Hypervisor on ARM64 UEFI and ACPI. I will give an overview of Cloud Hypervisor project at first, including the background, architecture, and milestones. Then Henry will introduce what is ACPI and how it works on Cloud Hypervisor. Next, Jianyong is going to tell how EDK2, the open source UEFI, works with Cloud Hypervisor. At the end of the presentation, a demo with everything put together will be shown. Before coming to Cloud Hypervisor, let's start from virtualization. Virtualization is one of the core techniques of cloud computing. It can help divide system resources into VMs and provide fault and security isolation at hardware level. On top of hardware is the virtualization layer. Hypervisor, like KVM, Zen, or Hyper-V, works in this layer. Virtual machine monitors works with hypervisor to manage VMs. Above the hypervisor layer is the workloads. Usually, in a data center server, a large number of VMs can be created and run. The real workload is deployed in a virtual machines instead of on bare metal. Cloud Hypervisor that I am going to talk about today is a kind of VMM software. Now let's see what it is. Cloud Hypervisor is an open source virtual machine monitor. The project was started by Intel company in 2019. The project focuses on running modern cloud workloads. It supports ARM64 and x86 architectures. For Hypervisor, KVM and Microsoft Hyper-V are supported. As the project focuses only on running the workloads in data center, Cloud Hypervisor is strong in higher virtualized devices, but pays little attention in simulating legacy devices. Cloud Hypervisor is implemented in Rust language and is based on rust-vmm components. Why Cloud Hypervisor choose Rust and rust-vmm? Rust language is becoming more and more popular. It is designed for performance and safety. The well-designed memory model makes Rust free from memory corruption and memory leak, and Rust has good community support. Rust-vmm is a collection of software components that can be used to develop virtual machine monitors. They can handle the virtual machine memory, kernel, devices, and so on. To build your own VMM, you can simply invoke the functions of rust-vmm for the common functionalities of running VM. You only need to pay attention to develop your own logic. Now let me introduce what's inside Cloud Hypervisor and how everything works together. About hardware and the host kernel is rust-vmm. Cloud Hypervisor is on top of it. Now, two types of hypervisor are supported, KVM and Hyper-V. A crate named hypervisor was defined to align the interfaces, so other parts of the Cloud Hypervisor can be agnostic to specific detail. About hypervisor crate, there is a VMM crate. Here we have the source code for ACPI, device management, memory and vCPU management, interrupts, and the code for both architectures, and so on. For devices, a small number of legacy devices are emulated in Cloud Hypervisor, like Serial, GPIO, etc. For pyro-virtualized devices, so far Cloud Hypervisor has supported most popular VirtIO devices. We used to support both PCI and MMIO for VirtIO transport layers in early stage. But now VirtIO PCI is the only option because PCI is predominant in modern operating system, especially in data center. Besides the basic VirtIO devices, Cloud Hypervisor supports vhost user. It can also work as a standalone vhost user backend. To the right side of the diagram are the firmwares that Cloud Hypervisor works with. The Rust Hypervisor firmware is a very simple one that can load the bootloader from a disk image. It is part of Cloud Hypervisor project. The well-known firmware indicator began to officially support Cloud Hypervisor from the middle of 2021. This page shows what have been achieved on ARM and our plan for future. We began to enable Cloud Hypervisor on ARM since release 0.8. At the first version, only MMIO devices were supported. After that, more features were added gradually, like PCI, SciComp, snapshot and restore, and vhost user. Besides VirtIO, we also implemented all the commonly used legacy devices on ARM. For example, UArch and GPIO. In the first half of this year, we enabled the ACPI and EDK2 support. That was a big step towards modern virtualization. In future, we will enable more features on ARM, including IOMMU, VFIO, device hotplug, and the Rust-based firmware. We will begin to measure and optimize the performance as well. Next, I will hand over to Henry for the development of ACPI and Cloud Hypervisor. Thank you.
Thank you, Michael. From here, I'm going to introduce how we developed the AArch64 ACPI for the Cloud Hypervisor project. First, I would like to introduce some basic knowledge of the ACPI. The ACPI specification is an industry standard that provides a standardized operating system agnostic description of a computer's configuration and its various components. It also provides platform interfaces for power and system management. From the software perspective, ACPI defines a generic hardware programming model of the operating system. The ACPI machine language is the language processed by the ACPI AML interpreter. It is the bytecode of ACPI tables and ACPI control method that can be utilized by the ACPI. Normally, AML is firmware provided and platform independent. For developers, we are more familiar with the ASL, which is the short for the ACPI source language. Normally, an OEM or platform firmware vendor needs to write ASL and be able to single-step ASL for debugging. Then use the ASL translator to generate AML for the AML interpreter. The AML will eventually consumed by the OS. Based on what we have just talked about, how can we generate the AML code in the Cloud Hypervisor project? It is known that the Cloud Hypervisor is written in Rust, which is the high-level general purpose programming language. A trait in the Rust language tells the Rust compiler about functionality a particular type has and can share with other types. We can firstly define the AML trait, which contains a method called toAMLBytes, and then define the data types. Here, I only use the byte data type as an example. Users can extend to any data types needed in the ACPI specification, such as path, ERSNA, address space, etc. After this, we can implement the AML trait for the data type. This is basically implementing the toAMLBytes method for each data type according to the ACPI specification. Now we have the AML code. We can define our ACPI tables. The way Cloud Hypervisor project defines ACPI tables is that we can define a generic abstraction of ACPI tables called SDT. Then we implement method of this abstraction. Here, I will give an example of how the SDT table is implemented. Firstly, we will use the new method of the SDT abstraction to create an empty table with only headers passed by the new method. The parameter of the new method contains information we need for the ACPI table header, such as signature, table length, revision, and OEM informations. Then we can use the append slice method of SDT and the two AML Basics method of data types to append the content of the ACPI table. For DSDT, we will need the device, CPU, and memory information. As the append slice and two AML Basics methods are implemented following the ACPI spec, which means the table length and table checksum will be updated dynamically. Therefore, we can directly return the table after this. Based on what we have discussed, I will now introduce the ACPI tables in the Cloud Hypervisor and the work we did for the AArch64 platform. Firstly, I would like to introduce the ACPI tables shared by both x86 and AArch64 platforms, and they are DSDT, MADT, FADT, and MCFG. The DSDT table describes the devices, CPU, and memory of the system. On ARM64, what we added to this table is some ARM-specific devices such as PL011. Also, we tailored some method in the CPU definition block due to limitations on ARM. The MADT table basically describes the interrupt controller. On ARM64, we added the AArch64 gig structures, including gig distributor, read distributor, CPU interface, and ITS. For the FADT table, we added the AArch64 PSCI configuration at byte 129, which allows the VMM to manage the power status of the guest. Also, multiple vCPUs can be brought up using PSCI. For the MCFG table, we added the end PCI bus number, which is mandatory on ARM64. Also, there are 4 tables which are currently used on AArch64 platform only, and they are GTDT, SPCR, IORT, and PPTT. The GTDT table describes the AArch64 generic timer, and this is mandatory on AArch64 platform. Currently, we have enabled the generic timer for secure, non-secure, virtual EL1, and non-secure EL2. The SPCR table describes the serial port and console configuration. Since ARM has a dedicated UART controller PL011, and this UART controller is required by the ADK2 firmware, the SPCR table is usually mandatory on AArch64 platform. The Cloud Hypervisor project is targeted for modern cloud workloads, and therefore PCI and MSI should be supported. The AArch64 gig has the ITS, which is the short for the interrupt translation service for that. To support gig ITS and PCI, on ARM, we need the IORT table. Current IORT table basically describes the gig ITS and the PCI root complex node. The last table required on ARM is the PPTT table. This table describes the CPU and cache topology on the system, and the CPU topology support will be supported by this table. All of these are the ACPI supports that is currently in the Cloud Hypervisor. Now, I will hand over to my colleagues to talk about the UEFI support.
Hello, everyone. I'm Jianyong from ARM. In the following, I will show you something about the enablement of UEFI for Cloud Hypervisor on ARM64. The first thing, what's UEFI? UEFI is a unified extensible firmware interface. It's just a specification that defines software interface between an operating system and platform firmware. It can be considered a replacement for the legacy BIOS. It will bring rich function and security feature. The right picture shows you the UEFI boot chart. You can consider the UEFI as the first application of the system, and it will take responsibility to boot OS. Why we need UEFI on ARM64? The most important thing for us is to enable ACPI, as ACPI is based on UEFI. Also, with the ACPI, we can get some hotplug features, except for ACPI. The UEFI will bring the safety feature for the system. The red picture will show you the UEFI ACPI boot. We can see that ACPI will be prepared in the Cloud Hypervisor and will be installed at the end of UEFI boot. At the beginning of OS boot, the ACPI will be initialized. Next, how to enable UEFI. There are two ways before us to support UEFI. As the Cloud Hypervisor is Rust-based project, we can also create a Rust-based UEFI project for ARM64 from scratch. It will get better on safety and performance, but it is too difficult to start. So we choose the second choice, develop a UEFI for Cloud Hypervisor based on EDK2. EDK2 is a modern, feature-rich, cross-platform firmware development environment for UEFI. So we can reuse lots of code and save lots of efforts. But we will get less safety compared with Rust. To support the UEFI for Cloud Hypervisor in EDK2, first we will prepare the memory initialize library. As for the different platform has its own memory layout, we must prepare its own memory initialization library. Then we should adapt the device driver between Cloud Hypervisor and EDK2. The most important, we must re-implement the ACPI installation library, as there are no common ACPI installation library in the EDK2 for now, for ARM64. After all this driver and library code done, we must prepare a makefile for this project. In the EDK2, there are DSD files and FDI files can be considered as the makefile. We needn't create them from scratch. We can just base on some template and then modify on it. After all this code done, we can try to build it and fix the error. After we build success for it, we can get a UEFI image, and we can do the integration test by integrating the UEFI image with the Cloud Hypervisor. This flow chart shows the development work for us. We prepare the makefile first and build it. We will get lots of error for the first time. Then we must fix the error. The error may come from memory part, driver part, ACPI part, or the makefile part. After lots of round fix, the the fix work, we will successfully build the UEFI. After get the UEFI image, we will integrate it with the Cloud Hypervisor. Then we will get lots of error, and we will get back to fix error and build again, and round after round. At last, we successfully get the best UEFI image, and it works well with Cloud Hypervisor. Now, all the patches for the Cloud Hypervisor and EDK2 has been upstreamed, and this code has been merged. So we can see the UEFI and ACPI has been officially supported by EDK2 and Cloud Hypervisor. What we will do next? Because the Rust has better performance, and Rust-based UEFI will be smaller than the EDK2 one. So we want to create a Rust-based UEFI for Cloud Hypervisor. Then we will get better on safety and performance. Also, we will do some hotplug enable work, like memory hotplug and CPU hotplug. In the end, I will show you a demo for start UEFI and ACPI using Cloud Hypervisor on ARM64. This is ARM64 platform. Command line. Start it. This is UEFI boot. Then the kernel boot. The systemd service. Log in the system. We will show you the ACPI initialization log. Okay, that's all. Thank you.